In this lecture, first we want to see to implement a loop which checks if the first variable is smaller than the other and then print something on the screen, as we did in the previous lectures for other conditions. So first I say a is equal to 1, b is equal to 2. Now I create a loop. I say while a is smaller than b, then I want to print some string like hello world and hit enter. As you see, we have a loop. Now the question that we have is that how some instruction like this, a is smaller than this, some condition like this has been implemented in Python, or what kind of instructions does these instruction gets translated to at the machine level. So in here we go in the assembly, we did something like this for variable a being bigger than or equal to. Now we want to create or implement the third block of data which checks if the first variable is smaller than the second. So again, we want to just write them in separate blocks. So I say move r10 and 1, or actually I want to just change the r10 to be smaller than r9. We have a couple of instructions to work with that. We could use the sub to subtract the 2 from another value like 1 or 0 to make it 1 or 0 to be smaller than r9. We could use move, but I want to use another instruction so that you would know more instructions. I want to use zar or XOR. I say zar r10 and r10. This command would make the r10 content to be equal to 0. Why? If you know about the basic logical operators, I guess we have like AND or XOR or zar, which are the important one. For example, in the AND, if we have 0 for the A, 0 for the B, A and B would be equal to 0, or let me actually show them to you in here. If you have A in here, B in here, and A, and B in here, it would be equal to just 0 in here. If we have A equal to 0, B is equal to 1, still we would have 0. If you have A equal to 1 and B equal to 0, we still have 0, and the only case that the output would be 1 is if both of them are 1. For the OR, this what happens is actually, let me just show the OR to you also. If we have A or B, what would happen if both of them are 0? We would have 0 in here. If A is equal to 0, B is equal to 1, we would have 1 in here. If A is 1, B is equal to 0, we still have 1 in here. If both of them are 1, then we would still have a 1 in here. But about the zar, it changes. If you have A zar B, what happens is that if A equals 0, B is equal to 0, then you would have 0 in here. If A is equal to 0, B is equal to 1, then you would have 1 in here. If A is equal to 1 and B is equal to 0, we would have 1 in here. If both of them are 1, then you would have 0 in here. If you pay attention to the zar operation, the reason that I wanted to talk to you about AND and OR, because there are actually some logical operations with the same name and OR, which you get the output like here. But what this happens that we want to use the zar operation in here. If you look, it says the output would only be 1 if the inputs are not the same. But if they are the same, it means if A and B, both of them are 0 or both of them are 1, then we would get a 0 in here. So in here, when we zar r10 with itself, we would get only 0 for all of them. And the reason, if you look, r10 is equal to 2, right? So if r10 is equal to 2, for example, let's say we have 0, 0, 0, 0, and so on, and then 1, 0. This in binary we know is equal to the decimal 2. So if we zar it with the same value in here, then because all of them are the same, the zar would be equal to 0. Well, 0 and 0, it would be 0. 1 and 1, it would be 0 again. 0 and 0, it would be 0, 0, 0, 0, and so on. So all the contents of the r10 register would be equal to 0. So in here, now that we have XORed R10 with itself, the R10 register would be, the content in the R10 register would be equal to 0, even though the content of R9 is still equal to 2, but I want to move the 2 again to the R9 because we want them to in separate blocks. And then I want to compare the R10 and R9 in here and use another jump. But because I don't want to jump in here, I say JNE so that it won't jump because of these two instructions. If you want to make sure of that, I just save it, exit, and let me just assemble it again. And now we execute it, and if you look, nothing has been executed. You won't have any, nothing has been printed. You won't have any kind of loops in here. Now I want to implement it using another jump. There are two kind of jumps. One of them is JC. So I say JC printing. JC would look at the carry flag. If it is set, then it would jump. And because we are subtracting 2 from 0, in here we have 0 minus 2. So the carry flag would be set. If I just assemble this and link this again in here and execute it again, you see we have an infinite loop. There is another command also which checks if the first one is smaller from the second one, which is the JB, which means jump below. So in here I save it, I assemble it and link it again and execute it. You see again we have an infinite loop. So using what we have been explaining in the previous lecture, you could say that JZ is equivalent to JE because JZ just looks at the 0 flag. If it is set, it knows that the result of the last operation has been equal to 0. So JE is equivalent to that because JE also means that jump equal. On the other hand, we have JB, which means jump below. So when do we have jump below? The first one is smaller than the second one when the carry flag is set. So we could say that JC, which looks at the carry flag, and JB are equivalent because JB also looks at the carry flag. And at last we had the JA, which means jump above, and that would look at the 0 flag and carry flag. If they are both 0, then it knows that well, the first one is bigger than the second one. We could say that it is equal to JA is equivalent to, for example, JNC and JNZ. So now let us just debug this, or go to the debugger and step through different instructions. Also for the last one in here, so I press Ctrl O and hit enter. I also go to another file and say obj dump in here, and then compare, hit enter, and we go to the GDB and compare. We start a break at a start, we run it, step through it. Well, I'm going to just pass a couple of steps in here. Right now we are at 4000 DC, which is this one. We want to get to the 4000 ED. So I just say step E, we won't have any jump. And now we are at 4000 ED, which is XORing R10 with itself. If I say info registers and R10, as you see, we have the number 2 in here. If I say step I and now check the R10 register, you see the value has been changed to 0 because of the XOR operation. Also, I want to have a look at the register E flags. Well, the ZF and PF have been set because of the previous instructions, but now we want to look at the carry flag, how it is changed. Well, after that we want to move the R9 register, even though R9 still it is 2, but we have an extra instruction in here, it's still 2. Now we are pointing to the 4000 F6. If you look, 4000 F6 is for subtracting or comparing. So I say step I, and now I check the eFlags register, if you look, CF has been changed or set to 1. Carry flag is actually the first bit in the rFlags or eFlags register. If we use our calculator in here to see the binary representation of 293, we see that the first flag, the carry flag, has been set in here. But well, we don't have the 0 flag set, which the third flag, if you look, it's not set in here. The third flag, the fourth, the fifth, sixth, and seventh, which means that the parity flag is also not set, and we have other kind of flags in here too. But the one that is important for us for now is the carry flag. Now we are pointing to the address of, let me go to the debugger. If I say info RIP, we are pointing at 4000 F9, which is this address. It says JB 4000 and B0. So the jump instruction would look at the carry flag, the first bit, this in here. If it is 1, then it would put the 4000 B0, this address, into the RIP register. If it is 0, well, it would leave it just unchanged, or the length of this operation in here would be added to the current RIP instruction, which is 2 bytes, and we would have 4000 and FB, and we would enter this exit system call. But because it is set, well, let's see what would happen. So we say step I. Now I look at the RIP register. If you look, we have 4000 B0. We are in here, and after a couple of other step I's, you would see that we are in the printing and printing the hello world for the first time, and then it would go on, and we have an infinite loop. As an exercise, you could work with other kind of jumps because we have other flags in the eFlags register. So you could just have a look at the eFlags register, see all the other flags like the overflow flag and signed flag, SF and OF, and see the related jump to that specific flag, and also try to implement such a program in Python also.